Russia just flooded 47,000 hectares of dead forest in Siberia. Scientists called it ecological suicide, but 5 years later, something impossible is happening. Satellite images show 127 new species thriving in what should be a dead zone. Carbon sequestration is 340% higher than anyone predicted. This accidental swamp, twice the size of Manhattan, might have just solved a climate problem we didn't even know how to fix. But there's a catch. Methane sensors buried beneath the surface are flashing red, and what they're detecting could turn this ecological miracle into a ticking time bomb. In this video, we're diving into one of the most controversial environmental experiments ever conducted, and whether Russia just discovered the future of carbon capture or unleashed something we can't control. Did you know that Russia is facing an ecological catastrophe called zombie forests? Across Siberia, 18 million hectares of dead and dying trees stretch across the landscape. That's an area larger than all of Florida. These aren't just dead trees. They're carbon bomb, bark beetle infestations, massive wildfires, and thawing permafrost have killed forests that once absorbed carbon dioxide, turning them into rotting hulks that release stored carbon back into the atmosphere while providing zero ecosystem services. The numbers are staggering. The 2019 to 2020 Siberian wildfires alone burned 19 million hectares and released 56 megatons of carbon dioxide, roughly the same as 12 million cars driving for an entire year. And it gets worse. Siberia is warming 2.5 times faster than the global average, accelerating forest death at unprecedented rates. Each year, the wildfire risk escalates, threatening settlements and infrastructure across thousands of miles. The dead biomass creates a blanket over the soil, preventing natural regeneration and creating permanent ecological dead zones where nothing grows. But these zombie forests stand directly in the way. Traditional removal methods are impossibly expensive, between $800 and $200 per hectare, and at 18 million hectares, that's a bill exceeding $14 billion. Even if Russia could afford it, conventional clearing creates its own environmental damage. The clock is ticking, international pressure is mounting, and Siberian forest collapse affects global climate systems. Russia needed a solution fast. Before we get to the radical experiment, you need to understand why every conventional approach failed. Clear-cutting and replanting sounds logical, but it's cost prohibitive at the scale needed. Even worse, newly planted forests require 40 to 60 years to break even on carbon, decades Russia doesn't have, and the process destroys remaining biodiversity, leaving barren landscapes vulnerable to erosion. Controlled burns seemed promising until they proved unpredictable. Fires designed to clear dead wood regularly escaped containment, releasing massive amounts of carbon dioxide and destroying soil structure. In Siberia's harsh conditions, a controlled burn can turn catastrophic in hours. Natural succession, just letting nature take its course, takes 80 to 120 years in Siberian conditions. Meanwhile, the ongoing fire risk continues, and carbon keeps releasing. Some proposed biomass harvesting for energy, but it's only economic near infrastructure. The energy-intensive transport removes nutrients from the ecosystem, and most zombie forests sit hundreds of miles from any facility that could process them. Every approach demanded decades to see benefits, while the climate crisis screams for immediate action. Russia needed something different, something bold, something that turned the problem itself into the solution. In 2016, Russian ecologists noticed something remarkable. Logged areas in western Siberia that had accidentally flooded showed unexpected biodiversity rebounds. Birds returned, wetland plants colonized, species that hadn't been seen in decades suddenly reappeared. What if, researchers wondered, flooding could be engineered at scale? The target site was the Khanty-Mansiysk region in western Siberia, 47,000 hectares of beetle-killed pine forest in the Ob River watershed. The location was strategic. Naturally low-lying terrain with clay substrate meant water would stay put. Proximity to existing research infrastructure allowed for monitoring. Isolation from major settlements. The nearest city sits 180 kilometers away. Reduced risk to populated areas. And seasonal meltwater from Ob tributaries provided a natural water source. The vision was audacious. Transform an ecological liability into an engineered wetland. Something they called the Siberian Pantanal. Dead trees wouldn't be removed. Instead, they'd remain as standing snags, becoming bird habitat while waterlogging slowed carbon release. The concept challenged everything conventional forestry taught. You don't flood forests, You drain wetlands to create forests. This was backwards. This was radical. This was 18 times cheaper than conventional clearing, with a project cost of just 2.4 billion rubles, about $26 million. Turning 47,000 hectares of dead forest into a functional wetland required serious engineering. The team constructed 23 kilometers of earthen berms, each standing 3 to 5 meters high, creating contained basins. 8 automated gates controlled water levels, powered by solar arrays to maintain independence from the grid. The system would redirect seasonal meltwater into the dead forest zones, maintaining water depth between 0.5 and 2 meters, deep enough to kill remaining trees, but shallow enough to create ideal aquatic habitat. But engineering a wetland in Siberia isn't like building one in Florida. The infrastructure had to survive brutal freeze-thaw cycles that crack concrete and warp steel. Spring floods could overwhelm the dams catastrophically. Ice formation threatened to damage control structures. The IA team built 34 kilometers of elevated roadways on floating foundations, allowing year-round monitoring access despite waterlogged soils. 3 field stations provided dormitories, laboratories, and drone launch sites for aerial monitoring. The monitoring network itself was impressive. 15 stations tracking water quality, methane emissions, and species colonization, integrated with Roscosmos satellite systems for quarterly high-resolution imagery and thermal sensing to detect methane hotspots. At 47 locations, automated methane sensors stood ready to alert researchers if emissions exceeded safe thresholds. Total infrastructure investment reached 840 million rubles, another $9.1 million. Initial flooding began in 2018 and 2019, with full implementation by 2020. Here's where the science gets fascinating. In normal conditions, dead trees decompose relatively quickly. Bacteria and fungi break down the wood, releasing stored carbon dioxide back into the atmosphere. But underwater, everything changes. Decomposition slows dramatically because oxygen, which decomposers need, becomes scarce. The waterlogged conditions create an anaerobic environment where organic matter breaks down at a fraction of normal speed. Think of it like this: a dead tree on dry land might fully decompose in 20 years. The same tree underwater might take 200 years. During that time, carbon stays locked in the wood instead of entering the atmosphere. Even better, as aquatic plants colonize and grow, they pull carbon dioxide from the air during photosynthesis. When they die, they sink into the sediment where low oxygen conditions preserve them, building carbon-rich layers year after year. Projections suggested the system could sequester 340,000 tons of carbon dioxide over 20 years, roughly equivalent to taking 73,000 cars off the road permanently. The slow-release approach meant carbon stayed trapped in sediments instead of hitting the atmosphere all at once. If the model worked, it could be replicated across 2 to 3 million hectares of dead Siberian forest, creating the world's largest engineered wetland network and removing millions of tons of carbon dioxide from the atmosphere. After flooding began, something unexpected happened. Life exploded. Researchers predicted maybe 34 species would colonize within 5 years. Waterfowl, a few fish, basic wetland plants. Instead, by 2023, they documented 127 species. Migratory birds that hadn't been seen in the region for decades suddenly appeared. The rare Siberian crane, a critically endangered species, began nesting in the flooded snags. Fish species from the Ob River migrated into the new wetland, establishing breeding populations. Wetland plants like cattails and sedges spread rapidly, their roots stabilizing sediments and filtering water. Amphibians colonized, insects diversified. A wildlife corridor formed, connecting previously fragmented habitats across hundreds of square kilometers. The standing dead trees, rather than being liabilities, became crucial habitat, nesting sites for birds, perches for raptors, and shelter for fish. Local indigenous Khanty people, granted traditional harvesting rights, began participating in monitoring programs. The wetlands attracted ecotourism interest from researchers and birdwatchers fascinated by this rare wetland ecosystem emerging in the taiga zone. Plans developed for a sustainable fishing industry once the ecosystem stabilized. Carbon credit revenue looked promising under international agreements. The project created 45 permanent jobs in monitoring and maintenance. What started as a desperate experiment to deal with dead trees transformed into a thriving ecosystem worth protecting. But beneath this success story, sensors were detecting something concerning: methane. The same anaerobic conditions that slow carbon dioxide release also create perfect conditions for methane-producing bacteria. And methane is a problem. It's 28 times more potent as a greenhouse gas than carbon dioxide over a century. Early readings showed episodic spikes up to 3 times normal levels. By 2023, total methane emissions measured 40% higher than models predicted. Some hotspots showed particularly concerning patterns. Researchers scrambled to understand what triggered the spikes. Was it temperature? Water depth? The type of vegetation decomposing? Nobody knew for certain. The monitoring system designed to track quarterly changes suddenly needed weekly attention in certain zones. The methane question threatens everything. If emissions continue rising, they could cancel out all the carbon sequestration benefits, potentially making the flooded forest a net contributor to climate change rather than a solution. Some scientists warned of a methane time bomb, decomposing organic matter underwater, slowly building pressure until catastrophic release. Others pointed to potential toxic algal blooms if nutrient balances shifted. The standing dead trees would eventually collapse, potentially damming water flows and creating stagnant zones where methane production accelerates. The harsh Siberian climate proved even more demanding than engineers expected. 2 dam sections required emergency repairs after the 2022 spring floods nearly breached the berms. One automated gate mechanism froze solid during a particularly brutal winter and remains non-functional, forcing manual management of that section. Economists project a $4.5 billion annual boost to GDP from agricultural productivity alone. Over 600,000 hectares of new farmland could be irrigated, turning Morocco from a food importer into a significant exporter. That's an area larger than the entire country of Brunei, suddenly becoming agriculturally viable. The job creation numbers are staggering. 350,000 direct jobs during construction and an estimated 150,000 permanent agricultural jobs once operational. But beyond the statistics, imagine what this means for actual communities. Villages in southern Morocco that have been slowly dying as young people migrate north in search of water. An opportunity could see complete revitalization. Rural families who've known water scarcity for generations. Tourism stands to boom as well. Water security enables sustainable tourism expansion across the south. Those ancient kasbahs, stunning desert landscapes, and mountain valleys could welcome visitors without fear of overtaxing local resources. Morocco sits just 150 kilometers from Europe, across the Strait of Gibraltar, perfectly positioned to become a stable agricultural supplier to the European market, but only if they can guarantee consistent harvests. The environmental benefits extend beyond human needs. Reducing over-extraction of groundwater could restore wetlands that have been drying up for decades and prevent the total collapse of aquifers that took millennia to form. There's even hydroelectric potential built into the system. As water descends from mountain heights, it can spin turbines, generating clean electricity as a bonus benefit. The harsh truth is that building through the Atlas Mountains presents challenges that would stop most projects dead. Morocco sits in a seismically active zone, requiring engineers to design flexible joints that can absorb earthquake shocks without catastrophic failure. Temperature variations in the mountains cause massive expansion and contraction in pipes. Materials must handle both freezing mountain winters and scorching summer heat without cracking or bursting. Many construction sites are so remote, they had zero infrastructure when work began. Everything, equipment, materials, workers, food, fuel, had to be helicoptered or trucked in over newly built roads. At elevations exceeding 4,000 meters, altitude affects both machinery performance and human workers. Equipment operates at reduced capacity in thin air, and construction crews need time to acclimatize or risk altitude sickness, affecting their precision work. Flash floods present another danger. Mountain valleys that look dry and safe can become raging torrents within minutes during sudden storms, threatening both workers and partially completed infrastructure. 3 tunnel-boring machines, each costing tens of millions of dollars, have already broken down in the harsh geology, requiring complete replacement. Yet after solving each challenge, engineers push forward, adapting techniques and learning as they go. So where does this mega project stand today? Phase 1, covering the northern section of roughly 400 kilometers, is 60% complete as of 2024. 8 pumping stations are fully operational, and 2 major tunnels are finished and flowing with water. Early sections are already delivering water to previously underserved northern communities, proving the concept works at scale. Phase 2, the Atlas crossing that represents the project's greatest challenge, sits at just 15% completion. The original 2025 completion target has been pushed to 2030, with some analysts suggesting 2035 is more realistic given current progress rates. Worker strikes over harsh mountain conditions have caused delays. Funding freezes have periodically halted construction as the government manages cost overruns. Initial water flow rates have come in about 30% below projections. Environmental organizations split. Wetlands International supports the project as innovative climate adaptation, showing how desperate times demand creative solutions. Greenpeace Russia demands a halt pending full environmental review, arguing that good intentions don't justify inadequate safety measures. Canada now explores similar approaches for beetle-killed forests in British Columbia. China sent a delegation to study techniques for Loess Plateau restoration. The European Union expressed interest in carbon credit validation if methane can be controlled. Western sanctions complicate everything. The Russian government struggles to access advanced monitoring technology. Foreign researchers face restricted access, limiting international collaboration precisely when multiple perspectives could help solve the methane puzzle. Yet if the project succeeds and methane gets controlled, it validates radical ecosystem engineering as a legitimate climate solution. If it fails spectacularly, it discredits nature-based solutions at a critical moment when the world desperately needs them. 5 years in, Russia's flooded forest defies easy judgment. The biodiversity explosion exceeded every prediction, 127 species thriving where death once reigned. Carbon sequestration hit 340% above projections in the organic matter trapped in sediment. A thriving wetland ecosystem emerged from ecological wasteland in just half a decade. Standing dead trees, once symbols of forest death, now cradle rare Siberian crane nests. Yet methane whispers warnings from below. Emissions 40% above predictions. Episodic spikes with unknown triggers. The possibility that all carbon benefits could be erased by this potent greenhouse gas. Infrastructure struggles under Siberian conditions. Budget cuts threaten monitoring. Political battles rage over expansion. The world watches one question. Will this become the blueprint for saving dying forests globally, or a cautionary tale of hubris? Russia faces a decision within months. Double down with Phase 2 expansion, or pull back pending methane solutions. The stakes extend far beyond Siberia. With 18 million hectares of zombie forests remaining and climate targets looming, Russia needs this to work. But more than that, the world needs new solutions. Conventional approaches failed. Time is running out. Maybe controlled flooding is visionary. Maybe it's reckless. Right now, it's both. So what do you think? Is this accidental ecological triumph or disaster waiting to erupt? Could engineered wetlands save dying forests worldwide? Or should we stick with slower, safer methods? Drop your opinion in the comments below and subscribe so you don't miss what happens next in this unfolding ecological drama. Because in Siberia's flooded forest, every month brings surprises, good and bad, and the final chapter isn't written yet.